Welcome to Data Science with EJD. Still talking about reinforcement learning. Our next focus shifts to model-free prediction, knowing that we cannot always get all the full information in every situation. In the last video, we looked at dynamic programming, which requires us to know every state and know the environment and all that. But that is not always possible, and that is why let's see what happens with model-free prediction and reinforcement learning. So the background is, of course, let's get the background. What is model-free prediction? So it is prediction problem in reinforcement learning. Estimate. So the goal is to estimate the value function v pi of s, which is the expected sum of discounted rewards when starting from state s and following policy pi. So v pi of s is that expected pi, for the summation from k equals 0 to infinity of y gamma raised to power k, and then r. Of course, I was trying to remember that in the last video. It's gamma is a discount factor, and then we have the reward, right, at t plus k plus 1, given that you have been at state s, that is. So of course, gamma belongs to 0, comma 1, one exclusive, one not included, because but you want to get to as close as possible to 1. So gamma is a discount factor, just like I said. So the model based versus model-free prediction. So of course, model-based uses known transition. So you are taking the probability of being in a new state, given that you've taken a particular action at a previous state, and the reward is based on the action you took at the previous state. So those are these two functions. So you use known transition P and reward R functions. Then model free is you have no knowledge, right? Uh, so dynamic programming, what we looked at that the other time, it requires it knowing all the possibilities. But here you don't have all the knowledge. So you have the knowledge of P or R and must learn from sampled episodes of experience. So we have the Monte Carlo prediction. So Monte Carlo methods estimate V pi of S by averaging actual returns observed after visiting state S in complete episodes. So it requires full episode trajectory until termination and suitable for episodic tasks. That's how Monte Carlo goes. Uh, so the algorithm steps down data collection. You sample full episodes following policy pi and return calculation for each visited state ST in episode. Compute the return. So you have G sub t equals the reward at t plus 1 plus discount factor multiplied by reward at t plus 2 plus square of discount factor, reward at t plus 3, and so on and so forth. So, and then you have the value update. So you update you update V at S sub t by averaging returns observed after visits to S of t. Then you have the incremental update rule, which is optional. So you have V of S plus alpha GT minus VS, being updated to VS, where alpha is a learning rate. We're talking about learning, right? Machine learning, reinforcement learning, and all that. So the properties of Monte Carlo prediction, it is unbiased because it uses the actual returns. It has high variance because returns depend on the full episode, which can be stochastic. You have delayed updates only updated at episode end. They have exploration requirement to cover all states effectively. So step 3 now, temporal difference prediction. So we have Monte Carlo prediction and we have temporal difference prediction, which is given as TD of 0. So the conceptual overview: temporal difference methods update estimate bootstrapping from current estimates instead of waiting for final returns. Of course, updates are done after each step rather than at episode end. That's opposed to what happens with Monte Carlo prediction. It is suitable for both episodic and continuing tasks. Okay, so the TDO update rule is this: at each step t, after observing transition st rt plus 1, s sub t plus 1, also you have v of st to be all that you have there. So where rt plus 1 plus gamma v of s sub t plus 1 is the TD target, the temporal difference target, and then you have the other one as the temporal difference error. That difference, that's rt plus 1, r sub t plus 1 plus gamma v into s sub t plus 1 minus v of st being the TD error. So properties of temporal difference. So you have it's bootstrapped, right? It uses existing estimates to update. It is biased, but with lower variance compared to Monte Carlo. Then it is online and incremental. No need to wait for episodes to finish. It is applicable to non-episodic tasks. So comparing Monte Carlo and TD methods, for prediction, right? So talking about requirement for episode end, Monte Carlo requires it, while temporal difference doesn't require that. Then update frequency. Monte Carlo comes after full episode, but temporal difference comes after each step. Then bias. Monte Carlo is unbiased because it gives true return, while temporal difference is biased because of bootstrapping. Then variance is high in Monte Carlo, but lower in temporal difference. Sample efficiency is less efficient with Monte Carlo. Uh, and sample is more efficient with temporal difference. So its ability, Monte Carlo is suitable for episodic tasks, while temporal difference is good for both episodic and continuing tasks. Convergence speed, Monte Carlo slower, temporal difference faster. Computational complexity potentially higher due to weighting in Monte Carlo, but it is lower because due to the fact that it works with incremental updates. Now let's do some practical application. Of course, in this case, we've been doing a lot of work. We've been doing some work on FrozenLake using a 4 by 4 grid. So estimating value functions in FrozenLake. FrozenLake environment description, it's grid world where the agent navigates slippery ice patches to reach a goal, right? So like you have to carefully. So on a frozen lake, you have to walk carefully because it's really slippery. Okay. So the state positions on a 4 by 4 or 8 by 8 grid, and the actions are left, right, up, and down. Challenges, stochastic transition, holes that terminate episodes. So if you get into a hole on the frozen lake, you can get stuck there, right? Sort of something like that. So we have the policy for prediction. You want to use a random policy or a fixed deterministic policy to sample episodes. So let's talk about a Python implementation in this case, talking about both Monte Carlo and temporal difference. So line numbers, right? Okay, so we need just NumPy and Gym. We've used Gym before. Gym is the place where where different reinforcement learning algorithms are tried. Below is a stepwise Python implementation of both Monte Carlo and temporal difference value prediction for frozen lake. So set random seed for reproducibility to ensure that you always get the same result. Then create environment with seed. So you have the environment gym dot make frozen lake minus v dash v1 is slippery true to make it stochastic, right? So then you have environment that reset seed for the two for reproducibility still, I believe. Then you define the generate episode, which involves the policy and the environment. So you have episode initialized here, and you have the state also env dot reset. So done is false, while not done. Then you have action policy at that state. The next state reward terminated truncated info and all that. And then you also do the Monte Carlo you do the Monte Carlo prediction, with all this coding, and then it returns the value of v. While you also do the temporal difference prediction separately, and then we can define random policy one action per state. So you have random policy np random dot choice and all that. So then random policy one action per state, you get that result. Then run predictions. Now you have VMC, that's Monte Carlo prediction with random policy and environment, and you have the VTDO, that's the temporal difference prediction uh, given the random policy and environment. And then we can print side by side for comparison. So I run this now, and then we see what that looks like. Okay. Right. So we have random policy, one action per state. So you have 230. So these are the possible action per state. So coming here now, we have state value estimate. So we have 16 states since we are dealing with a 4 by 4 thing. So we have 0 to 15. That's making 16 in all. For Monte Carlo, you have 0.059. For temporal difference, you have 0.023. Yeah, right. I mean, this message that looks like a warning is because of deprecation. It means in future versions of NumPy, this we won't be able to use what we currently have here. So you see all those results like that. You have some zeros, right? So those are points, terminal points, right? And then you have some values like that. So, and then you have values as high as 0.534 in this case. But in this case, you have lower values compared to Monte Carlo. So detailed explanation of the code now. So the generate episode simulates an episode under the given policy, returning a sequence of states and rewards. That's this function defined right here. It's a Python function defined here. Then MC prediction uses first visit Monte Carlo to estimate V pi, and it updates the value only for the first occurrence of each state in an episode. And you have the TDO prediction, of course, which implements the temporal difference, updating V at every step using one step bootstrapping. And then you have the random policy, which randomly picks actions for each state for demonstration purposes. So the interpretation of the results now, the general interpretation is that Monte Carlo estimates tend to fluctuate initially, but converge to accurate value estimates given enough episodes. Then the temporal difference prediction updates more frequently and may convert faster, but can be biased early on. Both methods provide approximations of the true VPI. TD temporal difference method typically perform better in non-episodic or infinite horizon tasks, just like we know. The Monte Carlo methods are useful when you want unbiased estimates and can afford to wait for episode completion. All right, so you don't have step-by-step updating. Therefore, based on the results we have here, what can we say, about the specific interpretation? So the value estimates show how valuable each state is under the random policy. States near the goal have higher values. That's like say 0.53, like this 0.53 now. It's closer to the goal than others like that. Um, so indicating a better chance of eventually reaching the goal from there. Then states with zeros or very low values are either holes or far from the goal, where the expected reward is minimal. So all the zeros we have, in all these results, all these zeros, in states, say state 3, state 5, and all the state 7, state 11, state 12, state 15. Okay, those are, you know, very low value. They correspond with very low values, which are either holes or far from the goal, and the reward is minimal at those points. Monte Carlo estimates tend to be slightly higher than the temporal difference prediction values because Monte Carlo uses full episode returns, while TD updates step by step. So you see generally that Monte Carlo values are bigger than the temporal difference values, right? So those are the specific interpretations. Overall, the values reflect the difficulty of the environment and the random policy's chance of success from each state. So you can see working on a frozen lake, especially when things are stochastic, can be quite a task. And that's why you have those small values. So the highest value you have for Monte Carlo is 53% chance, while for temporal difference, it's the highest you have is like 39. Yeah, I think it's 39.8, let's say 40% roughly. Okay. So summary and takeaways now. For model-free prediction, the key point is that you want estimating values from experience without known dynamics. All right. So things are easier if you have. I mean, if you can get all the necessary information about the environment and everything involved, then you can use dynamic programming. But since we can't always get that information, model-free prediction becomes pretty useful. Then we go for Monte Carlo, which uses complete returns, high variance, and episodic only. For temporal difference, it uses bootstrapping, incremental updates, and lower variance. Then for temporal difference at zero, we have simplest TD method, which updates after every step. Then we have frozen lake example, which is practical illustration with stochastic environment. Working on a frozen lake, of course, that comes with great skill and probably difficulty. Then Python implementation, so yeah, we had a real code demonstrating both Monte Carlo and the temporal difference prediction in action. So with this, we come to the end of that video. Let me know how helpful this is for you. All right. Let me also know if there's something you'd like me to try out. If you have not subscribed already, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. If you have subscribed already, thank you so much for that. We're already at 1,000 subscribers, and next we're going for 100,000 subscribers. I know the journey of 1,000 miles starts with a single step, and we are on our way. So let's make it happen together. Thank you so much for being here all this while. You can also become a member on my channel that with some perks like that. Just click on join and you find those possibilities. Don't forget my code sheets and my data sets, even my slides for presentations, like all the introductory topics. They are all available. If you can click on the link to Google Drive in the description box. You can get everything, download everything, and then I always advise that you follow step by step. So as I do it, you also go, especially when it comes to the coding area of things, right? Don't forget to like and share this video and other videos like this on my channel so that more people can have access to the great content I have going on here. Till I come your way again, Keep doing data right. Bye.